Hi everyone. So today we are going to solve one example problem for the discrete time Markov chain. So this time we are going to model the discrete time Markov chain model for the inventory system. Okay, some kind of inventory system. Okay, so here's the one that you are going to work on that. Is that too small? Let me merge. Is that big enough? Okay. Okay, so let's suppose you are a car dealer. Okay, you're a car dealer, and at the end of each day, let's say for a very special brand of car, let's say such as maybe Mercedes-Benz, Maybach is very expensive, right? Or if you want, you can go with sports car. Like, which car is the most expensive, by the way? I'm not sure. Is that Bugatti or Ferrari? I don't know. Something very expensive car you can consider, maybe. So anyway, let's say you're a car dealer of such a premium, very luxury brand of car. So at the end of, let's say, each day, at the end of each day, you're going to check the inventory level. Okay? So the decision is if the inventory level exceeds 1, okay? So I'd say that is the reorder point. So here, the first s, small s, is the reorder point. So right now, this small s is equal to 1. Okay? So if the inventory level exceeds 1, then no action is taken. Okay? Otherwise, which means if one or fewer cars left in the display room, then enough number of cars will be ordered to refill the display room. Okay? That has the maximum capacity of 5 cars. Okay? So here, the capital S is the max capacity. So here, the capital S is given as 5 in our case. Okay? And the replenishment will be done before the business reopens in the next morning. That is our assumption. So this problem is called SS inventory problem without backorder. In this case, backorder is not allowed. But next time, I'm going to give you another example for the inventory problems. But next time, we're going to consider the backorder. Okay? But keep in mind that today's example does not allow backorders. Okay? And the probability distribution of the demand is assumed to be the same for each day, which is like this. Okay? Okay, sorry. So now let's construct a Markov chain model based on all this given information. Okay. Okay. And here's our state of definition, state of system definition. Okay. The states are numbered 1 through 6, with state 1 represents the 0 stock on hand, 0 inventory level, and state 6 is 5 units stock on hand. That is a full inventory level. Okay. Okay, so let me use the smart board. Okay. So we define the state of system according to the inventory level, stock on hand, at the end of day, before replenishment is done. Okay? So let me just write it up. State number I and stock on hand inventory level for our Markov chain model. 1, 2, 3, 4, 5, and 6. We have 6 different state of system, and then inventory levels goes from 0 to 5, right? So keep in mind that we define the state of system based on the stock on hand level at the end of day before replenishment occurs. And also, daily demand for the car is random, and we are assuming that the probability distribution of the demand is same each day. So I'm going to just write it up because we are going to use this demand level and the corresponding probability. 0, 1, 2, 3, right? Is 20%, 40%, and 30%, and 10% each, right? And let's assume that the demand occurs only during the business hour. That is makes sense, right? So demand occurs only during the business hour. So basically we're going to have something like this. 1, 2, 3, 4, 5, and 6. 6 different system, right? 6 different state, sorry. And then for each state, inventory level is 0, 1, 2, 3, 4, and 5. Is that right? So starting from this state number 6 right here, let's see what transitions can occur. Okay? So here we're going to start from state number 6, which means given that the inventory level is 5, let's say last night, then we want to know how many cars left tonight, okay? Depending upon different demand.
So it has 4 possible.
Yeah, there are 4 different possibilities,
0,
right?
1, 2,
Right, right.
number of demands.
Right, that's true. So do we have this transition?
Yes, 0.2.
Okay. What is this probability? That's
Same level.
6 to 6, right? You start from state number 6, and then after one transition, you're coming back to state number 6, right? It stays there. So what is this? Probability is given the inventory level was 5 last night. Okay? The inventory level tonight is 5 again. Okay? Is that correct? Then when does this happen? If there is no demand during the business hour today. Does that make sense? No demand. During business hour today. Does that make sense? So we can visualize this situation. Let's say this is the timeline. And then let's say from here to here. Today is yesterday, okay? And then from here to here is today. Okay? So the business hour is, let's say, 8 o'clock in the morning until, let's say, 5 o'clock in the afternoon. Okay? So these are the business hours. So each day they work from 8 to 5. So these are the business hours. So we assume that the demand occurs only during this business hour each day. Okay? And you're going to check the inventory level at the end of each day, only once. Okay? So let's say the checking point is right here. This is the checking point. So let's say maybe 7 o'clock. Okay? Again, today the checking point is 7 o'clock in the evening. Okay? So here, this transition means this transition, right? 6 to 6 means last night when you check the inventory level here, you have 5 cars, right? And then tonight, again, you have 5 cars. That's because during the business hour today, there is no demand. Does that make sense? Right? So I'd say the same probability is equal to probability demand is 0. Okay? Does that make sense? Yes.
So beginning of the demand only occurs business hours.
Right.
So this one here is no demand at this time, is that what you're saying?
Yeah.
Okay.
Because there is no demand during this business hour today. Okay? So if you go to the top all the way, the probability that there is no demand is 20%. Is that right? So what is this? This is going to be 0.2. So probability for this transition is going to be 0.2. Does that make sense? Okay, then let's move on to the next case. Okay, now can I change the color? I believe so. Okay. Do you have this transition? 6 to 5? What is this transition? Yes. Okay, it's starting from 5 cars last night, right? And then tonight you have 4 cars, right? That's because there is one demand, right? Demand is equal to 1 during the business hour today. So it's going to be 1. What is that? Corresponding probability is 40%.
But that's still P66, no, right?
No, it's going to be 6, 5. Sorry, yeah, that's the point, right? 6, 5. So that's going to be 0.4. Is that right? So, if you want to build up one step or one stage transition probability matrix, something like this. It's going to be 6 by 6 matrix, right? 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and 6, right? So what he did is 6 to 6 is a 0.2, right? And 6 to 5 is 0.4. Is that right?
Yeah.
Okay, let's go back. So if we continue, let's change the color again. What is this transition probability? Now we're considering 6 to 4. So instead we have 4. 6 to 4. P64. That is starting from 5 last night. Tonight, only 3 cars left. Okay? So we have 3 cars left. That's because during the business hour earlier today, there is 2 demands, right? So demand is 2. Here. What is that? It's 30%, right? So here we have 0.3. So we have here 0.3. All right? Of course, we have one more options, right? Starting from state number 6. So I'm going to use pink. We're going to have one more transition. 6 to 2, right? That means starting from 5 last night, tonight, only 2 cars left. Because during the business hour today, there are 3 demands. Is that right? So this time, demand is 3. What is that probability? Is only 10% of chance, right? That is 3. So if you go back, this is going to be 0.1, right? Okay. 0.1. Of course, those 2 will not happen. Okay? And make sure summation of each row in your transition probability has to be 1, right? Which is true in this case. 0.1 plus 0.3 plus 0.4 plus 0.2 is 1. So now it seems okay, right? Okay. So okay. Now let's move on to the next case, next row in your transition probability matrix, which is, now we start from state number 5. So stock on hand level is 4. Okay, 3, 2, 1, and 0. This is 5. Okay. So do we have this transition 5 to 6?
What is normally
No way, right? Because if the inventory level is 1 or greater than 1, then no actions taken, right? So this is going to happen, never ever happen. What about this?
Yes.
5 to 5.
There is 0 demand.
There is 0 demand, right? That's going to be, again, probability. Stock on hand level is 4 last night. Okay, and then stock on hand level becomes 4 tonight. Okay, because there is no demand during the business hour today, right? So that is D equals 0, which is 0.2, right? So this is going to be 0.2. We don't have this, so I'm going to delete this part. What about this then? This is same as previous case. Demand is 1, right? Demand is 2. Demand is 3. Is that right? So it's like starting from column number 5, we have 0.2, 0.3, I'm sorry, this is going to be 0.4, 0.3, and then 0.1, 0, and 0. Okay? And then what about if we start from state number 4? It's going to be 0.2, 0.4, 0.3, and 0.1. Okay. Now let's work on, if we start state number 3, what's going to happen? Okay, so let me draw the transition diagram again. 3, sorry. So let me do this. 1, 2, 3, 4, 5, and 6. These are the inventory level. Below each state. Okay? Okay, so we start from state number 3. Okay? Of course, 3 to 3 is demand is equal to 0. Is that right? This is going to be demand equal to 1. Is that right? How about this then? 3 to 1. Of course, this is going to be demand equals 2. Now, what if starting from state number 3, which means last night you have 2 cars left, right? What if there are 3 demands during the day today? What's going to happen tonight? How many cars left? Still 0 cars left, right? Is that right? Of course, if we allow backorder, then this is okay, right? Starting from 2 cars last night, if there are 3 cars, I mean if demand is 3, then 2 minus 3 becomes negative 1. That doesn't make sense. Only if we allow backorders. But the problem is, in this example, we assume that backorders are not allowed, right? Then, actually, we cannot use this. Is that right? Instead, what happened? This transition should be this probability plus this probability. Is that right? Because you remember how we define the state of system? We define the state of system according to the stock on hand level at the end of each day before replenishment occurs, right? So here, although you start with only 2 cars last night, if there are 3 demands, because we do not allow backorders, tonight only 0 cars left, right? It's not going to be negative 1. Negative number in the inventory level means it's in backorder. However, since we do not allow backorder in this example, we don't need to consider this. Does that make sense? Okay? So actually, this is what? Summation of these 2 probability is going to be 0.4, right? So up here we have here 0.2, 0.4, and then down here we have 0.4. Okay, so this is the tricky part. Is that right? And then, of course, you have all 0 values down here. Does that make sense to everyone? Are you following me? Okay. Now, let's deal with the situation where there is only 1 car left last night, which means we reach the, not here, we reach the reorder point, right? This example, the reorder point is 1 in this example, right? So let's deal with that. So let's go back to the problem description here. So according to the problem description, when you check out the inventory level, if one or fewer cars left or remain, then enough number of cars will be ordered to refill your display room. That is the maximum capacity of how many cars? 5 cars. Is that right? So we're going to stick to this rule at the moment. So let's do this. Again, let me draw picture here. So from here to here is yesterday. Then from here to here is today. Okay? And we have business hour. Okay? These are the business hour. Okay? And then at the end of the day, you're going to check your inventory level, right? And also we assume that all the replenishment will be done before the business reopens the next morning. Okay? So when you check the inventory level last night, if there is only 1 car left here, the stock on hand level is 1 last night, then how many cars you're going to order? 4 more cars, right? So that maximum inventory level becomes 5, right? I'm sorry, so your display room will be filled up, which has the maximum capacity of 5, right? So here at the moment, last night, you have 1 car left. So you're going to order 4 more, right? And our assumption is all the replenishment will be done before the business begins, reopens the next morning. So let's say all the replenishment will be done right before the business reopens tomorrow morning. Okay? So at this moment, your stock on hand level becomes 5. Okay? That's our assumption. So we'll keep this in mind. Let's do this then. So here I'm going to say 1, 2, 3, 4, 5, and 6. And stock on hand level is like this: 3, 2, 1, and 0. Those are the inventory level for each state. So we are talking about what if we start from here, okay? Which means what is the probability? 2 to, let's say, 6. What is this probability? 2 to 6. This is probability given only 1 left last night, right? So stock on hand level was 1 last night. Then what is this? Tonight you have 4, right? Inventory level becomes 5 tonight. What is this?
4.
Mm-hmm.
Demand is 4, right?
0.2 times.
Again, if only one car remained last night, the shelf is filled up overnight, right? Of course, before the business reopens the next morning. So stock on hand level becomes 5, right? Tomorrow, early in the morning, it becomes 5. Is that right? Because I just mentioned that, right? If the replenishment is done tonight, then early in the morning, tomorrow early in the morning, you have full inventory level of 5. Is that right? And then tonight, you have full inventory level. Is that right? From here. That's because during the day today, during the business hour today, there is no demand. Does that make sense? Okay? So this is same as stock on hand level is 5. Given stock on hand level was 5. And we can say demand is 0, which is 20%. That makes sense? So this is 0.2 in our case. What about this then? Do we have this transition, 2 to 5? That means last night, starting from 1, tonight, you have how many? 4. This is P25. Simply saying that, given last night, you have 5, tonight becomes 4. Because during the business hour today, there is one demand, which is 40% chance. Does that make sense? So, what he did here, two to 6 is 0.2, and then 0.4. Of course, if you keep going, then the probability distribution would be something like this. If you compare this, the row number 2 with row number 6, what happened? It's exactly the same. Is that right? That's because once you reach the reorder point, the thing is you're going to order enough number of cars to refill the display room. That is the maximum capacity of 5, right? So that's why these probability distributions are always same. Of course, this case as well. Okay? So this is going to be again 0.2, 0.4, 0.3, 0.1, and 0 and 0. Because we assume that every time the replenishment will be done before the business reopens the next day morning. Okay? Because of this assumption, this is always happen. Does that make sense? Okay? So this is the one-step transition probability matrix we're going to deal with. So I'm going to give you this. Okay.
So since there is zeros, it's a regular like matrix? Or?
Yeah, it's regular. Yeah, you can check it out. Actually here,
Yeah.
if you look at the second power, third power, you can see that all of the elements are strictly positive, right? So this is regular matrix, regular Markov chain. Okay. Okay, so let me pull up this information. Okay, so I want to look at this. So this is the exactly same matrix P. Okay, so this is the one-step transition probability matrix P. Okay, and down here, this is P square and P cube and P to the fourth power, right? And then this is P to the fifth power matrix. Let me zoom out a little bit so I can see everything. Better. Okay. Now this is F square, right? You know, this is same as F1, right? P1 is always same, so I don't provide the F1. This is what? F to the cube, is that right? Yeah, this is cube. And then if you go down, this is F to the fourth power and F to the fifth power, right? And down here, I already provide you steady state probabilities. Those are pi i's, right? It's the same as this. And then down here, this is M matrix, mean first passage times. Okay? So we are going to use all of this information to answer for the series of questions. Yeah. Okay, so let's work on the first question. Question A. How do you answer this question? What is the probability that the demand each day is 1 unit? This is very simple question. If you go up here, just use the given information. Demand is 1 with 40% of chance, right? So this is 40%. Very simple question. Okay? Now, how do you deal with question B? On the average, what is the percent of the weeks in which there will be a stock out? What is stock out? Stock out means zero inventory level, right? What is that? If you look at the state definition here, state number 1 means stock out. Is that right? So how do you answer this question? Right. So you need to look at pi 0, right? Pi 0, which is this. That's what you need, right? So it's going to be 11.36%. Does that make sense? Right? So this is going to be 11.36%. But it came from pi 1. Okay, how about C then? Over a long period of time, What is the average amount of end of day inventory? How'd you get this? Again, refer to the state definition. Yeah. That's going to be 0 times pi 1 plus 1 times pi 2 plus 2 times pi 3 plus 3 times pi 4 all the way up to 5 times pi 6. That will give you the average amount of end of day inventory, right? So that's going to be, if I use summation, then I will take the value of 1 through 6, right? And then that's going to be I minus 1 times pi I. Is that correct? Which is 0 times pi 1, 1 times pi 2, 2 times pi 3, and so on. So this is going to be 5 times pi 6, right? Actually, you don't need to compute it because I already provide this down here. Okay?
PIX.
0 times pi 1 plus 1 times pi 2 plus 2 times pi 3, right? Plus 3 times pi 4 plus 4 times pi 5 plus 5 times pi 6. That is going to be 2.4045. Okay? Make sense? Okay? Okay. Now, how about D? In steady state, what is the number of days between evenings when the shelf is empty? That is the being recurrence time of being the stock out, right? So it's asking that how often the shelf becomes empty. Does that make sense, right? There is a mean recurrence time of stock out. So what is the average number of days between stock out? Because the steady state probability that stock on hand becomes 0 is pi 1, right? The frequency that the system visits the same state, state number 1. Therefore, the reciprocal of this. Is that right? So that's going to be 1 over 0.113636. So you should be able to get this. What is this value? Could you give me this value? What is this value? 8.9. So it's approximately 9 days, right? So I had to say once every 9 days, the shelf becomes empty. Okay, that's how I would answer for this question. Does it make sense? Okay. Okay. Okay, now how about question E? In steady state, what is the number of days between evenings when the chef is refilled? So he's asking how often the chef is replenished, right? So when does the chef replenish it? If one or fewer cars remain. Every time there is one car or 0 cars in your display room, then your shop will be replenished. Is that right? So I said every time if one or fewer cars remain, it will be replenished. Is that right? So the mean recurrence time of replenishment would be 1 over pi 1 plus pi 2. So could you give me this number? What is the 1 over pi 1 plus pi 2? That's 3.4? Okay. Thank you. So does that make sense, right? Because the steady state probability that the inventory is restocked is going to be pi 1 plus pi 2. So the frequency that the system visit the set of states 1 and 2 is therefore the reciprocal of these probabilities. That's why 1 over pi 1 plus pi 2 will provide you the desired answer. Okay? Okay, now let's move on to question F. If the chef is full right now, what is the expected number of days until a stockout occurs? So, if the chef is full right now, on the average, how many days are required until the stockout occurs? So, which information you're going to use? You're going to use mean first passage time, which is an M matrix, right? Because you start from full. So start from state number 6, you end up with stockout. So it's going to be M61, right? What is that value? M61. Here, M61. 8.8, right? That's going to be the answer. Make sense? Okay. Okay. Now let's move on to the next question. Is that G, right? So if the chef is full Monday morning, what is the expected number of days during the next 5 days in which the chef is refilled? Do you see the similarity of the questions that we've done last time? Okay. So do you remember? In this case, we defined decision variable, right? So let's say G5 is equal to 1. if the shaft is refilled. For the next 5 days, starting from full. No. Okay? Otherwise, it's going to be 0. Then we want to get the expected value of G5. Okay? Do you remember this? Right? Okay. So this is going to be 1 times this case, right? What is this? P starting from 4 today, and then it will be stuck out tomorrow. Also, 4 today, and then there is only 1 left tomorrow, because both of these cases it will be replenished, right? And then plus today was 4, and then 2 days later it will be stuck out. Today is 4, 2 days later only 1 left. Starting from today is 4, 3 days later it will be stuck out. 4 today, 3 days later, only 1 left. Continue on. This is what happened after 4 days. And then, finally, what happened after 5 days. Is that right? And plus 0 times 1 minus all of this. Right? So I can rewrite down using summation. That's going to be sum over n equals 1 to 5. P sub 6 1 nth power plus P sub 6 2. Is that right? Plus 0. So this is what you need. And I already provide you right here. What is this? That is sum over P sub ij nth power n equals 1 to 5. That is what we call expected number of visits during the first 5 stages, so that n takes only 5 different values, 1 through 5. Make sense? Okay? So what value we need to look at? We need to look at 6 1 and 6 2. So you need to add up these two numbers. 0.4358 plus 0.7264. That's going to be the answer for question G. Is that right? Okay, now let's move on to question H. Okay, if the chef is full Monday morning, which means it was refilled Sunday evening, Sunday night. Does that make sense? Right? What is the probability that Thursday evening the chef is empty? I said
60.
this tells you that it was refilled Sunday night. Okay? So starting from Sunday night until Thursday night. So how many days difference? 4 days difference, right? This is 4-day forecast. Is that right? Starting from Sunday through Thursday is 4-day difference, right? So you need to look at which one? P to the 4th power matrix. Starting from 4 and then end up with empty. So it's going to be 6, 1. So what is this value? So if you look at this, P to the power 4 matrix, 6, 1, which is this, 0.118. Make sense? Okay, so this is the last question then, question number I. If the chef is full Monday morning, again, this implies that it was refilled Sunday night. Okay? What is the probability that Thursday evening the chef is empty for the very first time? So these questions are similar. Only the difference is this part has been added. So instead of P, we're going to use F. All other information should be the same. Is that right? So if you look at P to the 4, no, I'm sorry, the F to the 4th matrix, which is down here, and 6, 1, it's going to be 1, 1, 3, 1.
Can you repeat that?
What?
Why you pick up in the next question? Why you pick up P61 and power 4?
Then what do you think, other? What is going to be the answer?
No, I'm not sure actually.
Oh, okay, you don't understand the problem? Here, okay, it does say if the chef is full Monday morning. So, it does say chef was full Monday morning. But, you know what? The checking time occurs only once per day. That is right after the business hour, right? At the end of each day, you're going to check your display room, right, inventory level. So if it does say chef was full Monday morning, which means it was refilled Sunday night. Okay? Yeah. So which means Sunday night, probably it was full. Okay? And then you want to know the probability that the Thursday evening, the chef becomes empty. So starting from Sunday instead of Monday, yeah. Starting from Sunday until Thursday, what's going to happen? And Sunday night, it was full, right? And Thursday night, it becomes empty. So that's why we're going to use 4-day forecast. So you need to look at the P to the 4th power matrix, and starting from full on Sunday and empty on Thursday. That's why you need to look at this. Is that right? Okay. Did I answer your question correctly? Okay. Yes.
But the last one is the first time, right?
Yeah, because of this term, for the very first time. That's why you need to look at the first passage probability,
Yeah.
first visit probability. That's the equal sign. Okay. Okay, so this is all for today. And next time I'm going to give you another inventory control type of problem. But next time we're going to deal with a little bit more complicated situation, because we are going to deal with the back order. Okay? Okay, thank you very much. See you next time.